Hi everyone, welcome to my presentation. My name is Cedric. I'm a PhD student at the Systems Group at ETH Zurich. I'm going to present to you our first steps towards building a continuous integration engine for machine learning models. Research in machine learning and systems mainly focused on two aspects in the last decade. The first one is speed. Researchers tried to tackle the question on how to train large-scale models with a huge amount of data faster and more efficiently by fully utilizing the underlying hardware. The second aspect is automation. Many leading tech companies released their AutoML system in the last few years. We in our group developed two small prototypes to tackle both problems for our users in academia and industry. With machine learning systems becoming faster and more automatic, we asked ourselves, is this enough for our users, especially those with little or no computer science background, to use the systems fully by themselves? We made a key observation there, and that is that for some of the users, if they're not really careful, they have nothing else than a more powerful, overfitting machine. So in order to prevent this, we wanted to provide some guidelines for the proper machine learning system usage. ease.ml CI is a first step in that direction. Our system is a continuous integration engine for machine learning models. You can think of it as being very similar to continuous integration engines known for traditional software engineering, such as Travis CI. In our context, we have a bunch of developers. They access a local development set in order to gain some insights and do some error analysis. We also have a shared repository where the current model active in production is stored. On this repository, there is a test set which is not accessible to the developers. Developers will then engineer and train a new model they want to push into production. In order to do so, they commit it to the repository. Our system will then make use of the test set in order to check whether the new model satisfies some requirement given in an additional file. After evaluating, either the requirements are fulfilled or not. If not, the system will return a failing signal and reject the new model. If the requirements are fulfilled, the system will return a passing signal and replace the current model in production. So what is hard about this? Well, there are two main challenges. The first one is we want to give rigorous guarantees but remain as cheap as possible. What do I mean by that? Our test set is used as a statistical estimator for the unknown underlying distribution. In order to have a high accuracy of this estimator, we would need a large test set. So we want both to have a high accuracy, but the test set should remain as small as possible. The second challenge is, even though developers have no access to the test set, returning a pass or failing signal on the requirements leaks information about the test set, and eventually developers will overfit to it. This is commonly known as adaptive analytics, and this is the main technical component of our system. The core results are statistically sound estimators to reduce the sample complexity by 1 or 2 orders of magnitude. Let me give you a more detailed overview over our system. We have two bunch of actors. On the one hand, we have developers which task only consists of engineer and train new, better models. The managers deal directly with the end user's need and specify the requirement every new model needs to have in order to become active in production. They both have access to a shared repository. Managers provide the test set in an encrypted, protected way. The training and validation data is made available publicly. So first, managers need to specify the requirements every new model needs to fulfill. Such a requirement could be, for instance, that all models checked in should have an accuracy higher than 80%. Remember that our test set is a statistical estimator, so we need to define the epsilon delta approximation we want to achieve. Developers' task consists of committing a stream of T model, and after every commit, they will get back a pass or failing signal. After T iterations, or when the test set loses its statistical power, the system will ask managers to provide n new test labels and downgrade the current test sets to be available for developers. As I said, managers need to specify the requirement in a given file. We currently support various types of requirements. One could be, for instance, that every new model needs to be better than the old model by at least 1% with high probability. We can also bound the difference in predictions between the new and the old model, or even have a simpler requirement where we only query the accuracy of the new model and ignore the accuracy of the current model active in production. We can also combine multiple requirements. Developer may only focus on engineering and training new, better models, and once they have one, they will commit it to the system. System will then evaluate and sometimes return a failing signal. Based on that insight, developers can re-engineer and come up with a better model and recommit. Eventually, they will hopefully get back a passing signal. As I said before, the core technical component of our work is adaptive statistical queries. This part of our work is inspired by seminal work given by the Ladder paper in 2015 by Blumenthal and by differential privacy work given by DeWork. What is adaptive statistical queries? Well, in adaptive analytics, you have an IID sample data points from an unknown distribution X. Developers have no access to that data. Initially, developers will commit the function f1, which can be seen as a function used to evaluate the accuracy or the difference in prediction. The system will then make use of that function, apply function g, and return its value to the user. This function g, in our case, is the binary signal of passing or failing the requirements. Based on that result, developers will come up with a new function f2. The system will reapply the function g and return the value to the developer. This goes on for capital T steps. The contract between the system and the developer is given by this epsilon delta approximation. Epsilon defines the size of the confidence interval, and 1 minus delta is the probability of falling inside this confidence interval. So the question we ask is, given epsilon delta and t, how large does our test set need to be? And can we decrease the dependency of n on epsilon delta and t as much as possible? For a single step, there's a simple solution in order to lower bound the number of samples we need. Hoeffding's inequality. If we define this probability to be equal to delta, we can simply rearrange and get a lower bound on n. For multiple steps, it's not that easy, but there are two main work which I will quickly mention here. The first one is our baseline approach, which basically resamples at every iteration and applies Hoeffding every single step. The second one is given by the Ladder paper, but it constrains on how G can evolve over time in order to apply those optimization techniques. To show you why this is not really feasible in our setting, let me give you an example for epsilon, delta, and t values which are reasonable in our context. Epsilon is set to be 0.01, the probability is 99.9%, and we set t to be equal to 32. I will stick with this number 32 throughout the entire presentation. Why 32? Well, if you think that developers commit a new model every single day, we will get the number of samples we need for an entire month. So the baseline approach would need roughly 1.7 million samples in our test set. And breaking it down to the number of samples per day, this is simply too expensive. The Ladder approach would be more feasible, but we cannot apply their optimization technique because in our case, G is non-monotonic. For the sake of completeness, I have to mention that there are other related work in adaptive analytics inspired by differential privacy. Nevertheless, we don't really know how to add noise to our G function in CI, so this will be future work. So our goal is basically to optimize the sample complexity for specific regimes that our system cares about. To this end, we provide a bunch of optimization techniques, and I will focus on the first and the third and the fourth technique in my talk. So the first observation is that the most trivial approach is usually not that bad. What do I mean by that? Well, in our setting, we know that our function g returns a binary signal. Based on that, we know the number of possible functions for t iterations is upper bounded by 2 to the power of t. So we can simply apply union bound to all possible functions. In terms of formula, we see that we get rid of the log t term, but we're still linear in t. This is not a big issue for us because we're not dealing with too large values for t. For the same numbers for epsilon, delta, and t as before, we know the baseline needs 1.7 million samples. We can reduce this by 1 order of magnitude by applying this trick. For the second observation, I focus on those type of conditions, which are the most popularly seen amongst our users. That condition has 2 parts. The second part bounds the difference in predictions between the new and the old model, and the first part requires new model to be better than the old model in terms of accuracy by at least 1 percentage points. While the first part is quite natural as a requirement, the second part ensures some quality and prevents undesired behavior when the end user uses the new model. We have 2 sub-observations here. The first one is, in order to determine the difference in predictions, we don't need labels at all. I will come back to that. And the second one is that conditioned on d smaller than 10%, we know that n minus o must have a small variance. We can make use of that fact by applying another well-known concentration inequality called Bennett's. By applying Bennett, we basically can reduce the 1 over epsilon squared dependency compared to Hoeffding. Again, with our set of parameters, the baseline now needs 7.5 million samples. Why is it more than before? Well, our condition is much more complicated, so we need samples to evaluate every part of the condition. With union bound, we can lower this by 1 order of magnitude, and applying Bennett's, we can lower it by a second order of magnitude compared to the baseline. So the last observation is that usually not all labels are useful. We've seen this for bounding the difference in prediction, but we can also apply this to bound the difference in accuracy. Let me show you an example. In this setting, we have 5 data points in a binary classification problem, which are unlabeled. The old model makes those predictions, and the new model predicts those values. So we see that the same predictions are not useful at all in order to estimate the difference in accuracy. So the question we ask is, if the new model and old model are only different in the prediction with certain probability, how many savings in terms of labels, not samples, can we have? And what we've seen is that if this probability is of order square root epsilon, the amount of labels we need is 1 over epsilon, compared to 1 over epsilon squared, the order of Hoeffding. So for a single signal, Hoeffding would need 15,000 samples, and having a probability of difference being equal to 10%, we would only need 2.2 thousand samples per signal, assuming that unlabeled data points are free. To give you an overview over actual numbers we can achieve, let me again look at the number of labels we need to provide for 32 models. We compare our baseline against the best optimization we can achieve in SysML CI. In the popular use case, we set epsilon to be rather small. For the most commonly used condition, we can decrease the number of labels needed by 2 orders of magnitude. And if you think about what 41,000 labels for 32 model means, breaking it down, this represents 1.3 thousand labels a day, which is not really much in order to get rigorous guarantees. For a simpler condition, the baseline requires less samples, but ease.ml CI is only able to achieve 1 order of magnitude saving, because we cannot apply all the optimization techniques here. If you're willing to increase your confidence interval size, the same conditions as above drastically decrease the number of labels we need. But we still have 2 order of magnitude saving for the most popular used condition, and 1 order of magnitude for the simpler condition. To give you a rough idea about how much 330 samples per day is, assume you have an engineer which is able to label a data point in 10 seconds. So this engineer would need to label data less than 1 hour per day in order to get those 330 labels per month. So I've presented to you ease.ml CI, our first approach to build a continuous integration engine for machine learning models. We are currently also working on a sister project, ease.ml Meter, which monitors the degree of overfitting on your local development set. Both systems are planned to be released this summer. Let me conclude by saying to you that we in our group think that if machine learning is truly software 2.0, it is time to define principles in software engineering 2.0. And we as a group hope that we can benefit from the SysML community in order to reach that goal. I thank you for your attention.
Questions? So I have a question. You said you have this system. Are people using it now, or it's not released yet? You haven't.
It's not released yet. It's going to be released in summer. We currently have it for our own users, but it's more of a prototype currently.
Okay.
Hi, Julio Zhao from Carnegie Mellon University. So I'm wondering if you had some thoughts on how some of these statistical techniques would generalize to more structured output spaces, like say object detection, or doing translations, or producing kind of masks, or basically things that are not categorical labels?
Yeah, so currently we focus on binary classification, that's true. We have ways to adapt this to multi-class classification, but adapting it to regression problem is still ongoing research.
Okay, thanks.
Thank you.
Hello. Thank you for this. This is absolutely wonderful. It's like an implementation of concepts, that I'm trying to communicate in my current project. So I plan to use it immediately. I'm wondering about the data sets actually for checking the models. Are you planning, how far into the future are you planning to support just one data set? And is that just, am I interpreting that correctly? In past implementations, because I've had to do this by hand, I've used numerous data sets, so I designed the systems to prevent regression problems. I'll have numerous data sets. So would that be something in the future to support?
Okay, so your question is basically, can we share the same data set for multiple models?
Yeah, and over time, as I'm collecting.
Yeah. So currently we focus on one model which is currently active in production, and developers provide a new model, which goal is to replace the current model, and we want to use that data set for those 2 models. So extending it to multiple models or different tasks is not something we have done yet, but it's definitely something we're thinking of.
Cool.
Hi, Evan from Quantum Black. I have a question from the examples you've shown there. It seems that you've put the data with the repository, like from the data sets.
Yeah.
Do you plan to have a way that you can have the data set in another system that's not accessible, or maybe you don't need to commit it in
So the only requirement is that the developer has no access to the data set, but our system, we plan to implement it as a service, similar to Travis CI, needs to access the data set and the committed model in order to do inference and predict the labels.
So essentially you would have a place to host the data set, and the data set will not be in the repository.
Yeah.
Okay. Thank you.
Thank you.
Okay, let's thank our speaker again.